So in this video, we're going to talk about the second derivative test. So this is similar to the first derivative test in that we are determining whether we have a local min or a max. But as the name implies, this time we're going to be using the second derivative instead of the first derivative. Another useful difference with it is that with the first derivative test, we needed information from around the point. So namely, we needed to know what the first derivative was around the point, meaning to the left of the point and to the right of the point. But with the second derivative test, we only need information at the point. So this can be helpful when you're dealing with complicated functions and it's hard enough getting information at the point, let alone around the point. I already have it written out here this time, so let's go ahead and read it first. So suppose that f prime of c is equal to 0. F double prime, the second derivative of f, is continuous over an interval containing c. Okay, so these are important conditions. So we need to be at a critical point, specifically one where it's equal to 0, not one where it's undefined at 0. Just undefined at c. And the second derivative needs to be continuous around on that interval. So if f double prime of c is greater than 0, if the second derivative at c is greater than 0, then f has a local min at c. So we kind of imagine what that would look like. So I have this little picture right here of what that would look like. Let me just kind of redraw it. So we can kind of imagine if we have a local min, the kind of shape it would have, right? So obviously the first derivative is 0 at that point. The second derivative being greater than 0 means that the tangent line at that point is underneath the graph, right? So that's going to happen when we have this kind of shape that we get from a local min. So on the other hand, if the second derivative is less than 0, then we would have a local max at that point. So same idea. Okay. So here it's concave down, right? Meaning the tangent line is above the graph, right? So that would give us a local max. And then finally, if the second derivative is equal to 0, the test is inconclusive. Okay. So in this case, we just can't tell either way. So we would need to then go to the first derivative test or a different alternative instead. Okay. So like I said, this one's useful because you only need information at the specific point, right? You don't need any information around the point. So like specifically in statistics, this is used a lot in like finding the maximum likelihood estimators, where you're anytime where you're finding a maximum of something, right? You're going to have this kind of thing because that's what we're doing. We're finding maximums or minimums. So it's often the second derivative test is often used to show that it is indeed the maximum likelihood estimator in that case. So let's go ahead and look at an example here. So let's just look at f of x equals x to the 5th minus 5x cubed. Okay. So the first derivative is 5x to the 4th minus 15x squared, right? So first of all, before we look at the second derivative, we need to find the points where the f prime of c is equal to 0, right? So we need to find our critical points first. So let's just go ahead and do that before we even bother finding the second derivative. So you could divide by 5 just to make it a little simpler. So we have x to the 4th minus 5x squared equals 0. We'll pull an x squared out, and we'll have x squared minus 5 on the inside, right? I think I did this wrong, right? This should be 3. That's my mistake there. So that should be 3 there, not 5, because we pull a 5 out. So now this means x squared equals 0, or x squared minus 3 equals 0. So this would imply x equals 0, and this would imply x equals plus or minus the square root of 3. So normally we would go for the first derivative test at this point, right? We would make a sign chart and we would see what it says. But now we're going to go instead for the second derivative. So the second derivative, first of all, we'll find it. So this will be 20x cubed minus 30x. Okay. And now we do need to verify that it's continuous. And we can just go ahead and state that outright because this is a polynomial, right? We know polynomials to be continuous, so there's no issue there. So now what we need is we need to determine at each of these points what is the second derivative. So we need to plug them in. Okay. So f double prime of 0, for example, is equal to 0. So this one is inconclusive. Okay. So via the second derivative test, we don't actually know what if this is a local min or a max, right? Or either. So we'll come back to that one. So we'll just look at the first derivative test or something. But let's go on to the other two for now. So let's look at the square root of 3. So we'll get 20 times the square root of 3 cubed minus 30 times the square root of 3. Now, at this point, it could be a little tricky to actually do this if you're not using a calculator. So we only really care if it's positive or negative. So maybe we could go ahead and instead of plugging in like this, maybe we could go ahead and like factor this first. So like, for example, we could pull out a 10x out of both of these, and we're left with 2x squared minus 3, right? So maybe we could plug it into that instead, because that's a little bit easier to work with for this purpose, right? Because now we know the outside is positive, so we really just need to know if the inside is positive or not. So root 3 squared is 3, so this is 2 times 3 minus 3, right? So 6 minus 3, which is 3. So this is positive, this part's positive, so overall this will be positive. In other words, this is greater than 0, right? So via the second derivative test, we have a local min at the square root of 3. Okay. So we have a local min. So then we'll do the same thing with the negative square root of 3, our last critical point here. So we'll just go ahead and plug it into that second part. Okay. So we already know this inside part is positive because the negative square root of 3 is also just going to be 3. And we just found that that's positive, right? So this part's positive, and this part is actually going to be negative. So overall, this is going to be negative, right? So this is actually less than 0. So by the second derivative test, we have a local max here. Okay, so we get a local min at root 3, a local max at negative root 3. And then at 0, it's inconclusive. So at this point, we'll just need to go back to the first derivative test to check if there is a local min or max at 0. Okay, so we can go back up to here, and we can look at the sign chart here for f prime. Now, if you're if you have read up on the multiplicities idea and how that affects the sign changes on a sign chart, you might have noticed the x squared is equal to 0. There's an even multiplicity here, which means that it's going to have the same sign on both sides of 0. So that's going to tell us that there is no local max or min, but we can just go ahead and check it anyway. So we really only need to look at, let's see, we can look at, again, we only need the sign, so we can look at 5x squared times x squared minus 3. Okay. So basically just this last part we had, but technically you'd have the 5 there, but that's not going to affect the sign anyway. So we only need to put in whatever number we want on both sides. So we can put in a 1, for example. So if we put in 1, this part is positive. This part is negative, so that's going to be negative. And if we put in negative 1, it's going to be the same thing because both of these are squared, right? So the sign's not actually going to change at all. So it's going to be negative on both sides there. Okay. So this means that there's no max or min at 0. And if you kept going, you would you should find that this has a plus and this has a plus, and then that also tells us that we have the local max and the local min. So anyway, so we try to do the second derivative test if we can, and then if it's inconclusive, then we have to go back to the first derivative test.